terminate. I will say my network is my slide is behaving somehow.
Just go to your first slide. You can control it using even the arrows on your keyboard. You can go to your first slide and then you start to present.
All right, sir.
Okay.
All right. Evening, everyone. So I'm going to present on Boolean algebra. So our learning objectives are understand the basic operations and laws of Boolean algebra, relate these operations and laws to circuits composed of AND gates, OR gates, inverters, and switches. Prove any of these laws in switching algebra using a truth table. Apply these laws to the manipulation of algebraic expressions, including obtaining a sum of products or product of sums, simplifying an expression, and or finding the complement of an expression. So Boolean algebra, it was introduced by John Boole, and this groundbreaking work, the laws of thought in 1854, laid the foundation for what we now call Boolean algebra, whose work was revolutionary because it was allowed logical statements to be expressed algebraically using symbols and equations, simplifying the study of logical reasoning. And so Boolean algebra is a branch of algebra that deals with two values, that is 0 and 1, or false and true, or sometimes it's on and off. So it's mainly used in logic circuits, computer science, and digital electronics. Boolean algebra became the foundation of designing digital circuits where 0 and 1 represents false and true, respectively. In modern computing, Boolean algebra, in modern computing, Boolean logic is essential in the design of everything from basic circuits to computer programming and data processing. So we have so there are three basic types of logic gates, which are AND gates, OR gates, NOT gates. We also have XOR gates, XNOR gates, and NAND gates, and NOR gates. So for the AND gate, there's usually a dot between the letters A and B. Like C, like here where it is said C is equals to A dot B. So this A dot B is represented by this AND gate. So we have A and B. We have A and B. Then we have this symbol, which is our AND gate. So which will give us a result C. So for the truth table now, we have A and B. Then we have 0, 0 for the value A, where we have 0, 0, 1, 1. In certain times, it can be represented as 0, 0, then true, true. Sorry, it can be false, false, then true, true. So here we have A as 0, 0, 1, 1, then B as 0, 1, 0, 1. So for our
So basically, it's like what we have done yesterday. This is a truth table, but now it's now under logic gets. So this is where I was said that normally here that's where we use the zeros and ones instead of T and F for true or a false. So if you are seeing a zero there, take it as false, and when I see a one there, take it as a true. And also it remains the case of creating the truth tables. It's just the same here. That's why you're seeing that we are actually having a false, false, then true, true. It's the same as what we were explaining yesterday when we're saying that when you're creating a truth table, use the half rule. It's either you start with the truths and then followed by false, or you can start by false, false, then true, true, something like that. It depends with the number of the statements that we have. For here, we only have A, B. That's why we've got 4 rows, and that's why we have got 0, 0, then 1, 1, and then a 0, 1, 0, 1 there. So basically, that's what we have. So he is applying the AND gate on the statement A and B. So if you look at it, you will see that it's the same as the one that we have done yesterday when we were talking about a truth table using the AND operative. And if you look at it, you could see that uh, you could see that that AND operative is just the same as the AND that we have here under the logic gates, something like that. So if you look at the one that we were doing yesterday, you could see that under propositional logic, you could see that the end through the table, the truth table for the end, you will see that it was only a true when we were having a both true on the two inputs. It's just the same here. We only have a one when we where we have the both truths. So Batra, you can take you can carry on.
all right, say thank you so much, say, for the addition. Then so we also have an OR gate, which is represented by this sign here. So it's basically, yeah, it is a difference here between it and the AND gate. There's this sign. So that's the OR gate, and it is the same again on the truth table as what we discussed yesterday in terms of the zeros and ones, as you can see on this truth table. So the output is true if at least one input is true. If both inputs are false or zero, the output is also zero or false. Then we have a NOT gate. Here now a NOT gate has got it's a triangle and this small zero here. So it represents a NOT gate. So for this symbol, we have A and C, A giving us which is equals to C. But now, because there's this NOT gate, it's no longer A, it's now A NOT or A disjunction. So this is the NOT gate. So the output is the negation of complement of the input. So it means if we have 0 here, we have an output of a 1. If we have a 1 here, we can have an output of a 0 here. So that's the NOT gate. Then we move on to the NAND gate. NAND gate is an abbreviation for NOT AND. A two-input NAND gate is a digital combination of logic circuits that performs the logical inverse of an AND gate. So here we have, let's say we have A here and B here. So if it's a NAND gate, if we've got 1 here and 1 here, our results by the end, it has to be 0. But if we've got a 0 here and a 0 here, our result has to be in a 1. So it performs the opposite or the inverse of an AND gate. So when you get a 1 on an AND gate, but on a NAND gate, it will be a 0. So the symbol is you have A dot B with an overline, or it can be A, B, then complement in brackets. So while an AND gate outputs a logical 1 only if both inputs are logical 1. A NAND gate outputs a logical 0 for this same combination of inputs. Then we have a NOR gate. The NOR gate or NOT gate or NOT OR gate is a combination of OR gate followed by an inverter. So we have here A and B. Then this is our usual OR gate, but now we have that small circle which is an inverter. So now it's now a NOR gate. So it's not OR. So here, same applies with the AND gate. Our input is the opposite of the OR gate. So if we have got a 0 and a 0 on the input for the NOT gate, now we have a 1. So if we've got a 0 and a 1, we have a 0. So it's basically the opposite of the result we should get when we have an OR gate.
So to make it simple for yourself, you can actually first work out the column for an OR gate, and then you just negate that OR gate to get the not OR gate, something like that, and then you get the output. That's the simplest way. So instead of just having A, B, and then the output, you'll be having A, B, and then you have the OR gate, and then you put the output there where you will be actually flipping the results of the OR gate, something like that.
All right, so thank you so much. Then we have the XOR gate. The XOR gate or exclusive OR gate acts in the same way as the logical either or. So its symbol is A plus, but it's in a small circle. Then the output is true if either input is true, but not both. So we have the output has to be true if either, like here, if we've got A and B, but we have A, which are B here, which is a 1, so our output has to be 1. But the output is false if both inputs are false or both inputs are true. Like for example, in our truth table, we have 0 here and a 0 there. Then our output is 0. Then we have a 1 here and a 1 on B. Then our output is 0 again. So this is the truth table of the XOR gate. For the sign, it says, you can see it's A, B, then we have this line before our all sign. Then that's A plus B. Then we have an XNOR gate. The XNOR gate or exclusive NOR gate is a combination of an XOR gate followed by an inverter. So it's a combination of this followed by this inverter. Our symbol is A plus B in a circle. Then we have an overline. This output is true if the inputs are the same and false if the inputs are different. So if we've got the input here is 0, 0, then our output has to be 1. So if we've got a 1 and a 1 here, our output has to be 1. So it says if we've got two inputs which are the same, then our output has to be 1 by the end. But if we've got one of the output which are, if our inputs are different, like here we have a 0 and a 1, then our output has to be a 0, no matter where the 1 or the 0 is. So they must both be the same for the output to be true. Then binary variables, Boolean algebra works with variables that can have only two possible values, which are 0 or false and 1 or true. These variables represent logical conditions like on and off, true and false. Basic logical operations with that AND gate or dot output is 1 if both inputs are true or are 1. Then, for example, we've got A dot B or then we've got A plus B, then our output is to be then we have the De Morgan's theorems. These theorems help simplify expressions involving complements and multiple variables. They are essential for converting ends or odds and vice versa when dealing with negations. Truth tables. A truth table shows all possible input combinations and their corresponding output. It's a crucial tool for understanding how a Boolean expression behaves. Simplifying Boolean expressions. Use laws and theorems to reduce complex expressions into simpler equivalent forms. Simplification makes designing logic circuits easier and more efficient. Then we have the logic gates. Logic gates are the ones which you have talked about before. They are physical implementation of Boolean operations in circuits. These basic gates are aimed on the not derived gates include NAND, NOR, XOR, and XNOR. Then we have canonical forms. Canonical forms are standardized ways to represent Boolean expressions. So with sum of products. For example, with a complement b, then plus ab. So this is a sum of products because we have an ab here and then a negation b. Then we have a product of sums. That's, for example, we have a plus b in brackets, then we have times a plus c complement. This is a product of sums. So we have K-maps. Maps are visual method for simplifying Boolean expressions. They are particularly useful for simplifying expressions with 3 or more variables. By mastering these concepts, you will have a solid foundation in Boolean algebra and be able to design and work with digital logic confidently. Then we have binary variables. Binary variables can only take 2 values, which are false and true. I think we've talked about this before. Then if A is equal to 1 and B equals to 0, then A negation is equal to 0 and B negation is equal to 1. So it's the opposite of the original value. So this shows how binary variables work with complements. Then we have the basic logic operations. The basic logic operations are and or not. Then we have the truth table here below illustrating these operations. So for a NOT gate, as we have said before, if A is 0, then A complement is 1. If A is 1, then A complement is 0. Then we have the inputs for the A and B here. So if we've got A0, B0, then our AND gate has to be 0. Then our NAND gate has to be the opposite of the AND gate. So it has the value 1. Then if it's, then our OR gate again has to be 0. Then our NOR gate has to be 1. Then XOR gate has to be 0, then XNOR gate has to be 1. So it follows again these values as we have said before. So we have the absorption law. So for the absorption law, it says if we've got A plus AB, our result has to be A. Then we have the De Morgan's theorems.
Before that, maybe you can try, or maybe you can try to explain why they are similar. Maybe there is a proof there, but you've done a rush through job. Yes.
All right, say, let me find a.
I'm not seeing there was there were tables there that we were seeing, but I'm not seeing them now.
Oh, here. The tables before.
No. Go on
Yeah.
the next slide. Go on the next slide.
It's on the De Morgan's law.
Under absorption laws, you do not have.
Yes, sir.
Okay, but the slide that you sent to me, you've got those things. Maybe you've removed them because you are not understanding them. But anyway, that one is the absorption law. You can try to go and find why is it the same or the way it was approved. Please, guys, you have sent me a slide with that information. So I know you have that information. Please, after the presentation, share it with the class so that they could do. Yes, you can try to do it. I thought you have the diagrams or whatever so that you could just show us maybe why do we end up there.
All right, sir. So here, if we can take A from this, then we put A outside the brackets, we will remain with 1 plus B. So according to the now elements, 1 plus B is equal to 1. So here, our result here will be A, then 1 here. So that's when our result has to be 8 by the 8. Then for the De Morgan's theorems, they help simplify expressions involving complements in multiple variables. You can find the same concept in the set theorems again. So if you can grasp it here, it will be easy. Even if in a set here now, you have an A union B instead of an A plus B, it will be A union B. So if you say A plus B complement equals to, it will be equal to A complement dot B complement. So even if it's in sets, it will be A complement intersection B complement. So theorem 2 again, if you have A dot B in brackets, then complement is equal to A complement plus B complement. So know that when, when this complement is inside, also the sign has to change. So be very careful about that, even when you do your set theorem. Then, for example, we have here A dot B complement. So using the De Morgan's theorem 2, it will be equal to A complement plus B complement. So for the truth table, we have A0, B0, then A plus B complement, we have 1, then A complement, because we have a 0 here, it will be 1, then B complement, because it's a 0 here, we have a 1 here. Then if it's A dot B, A complement dot B complement, it will be a 1, because it has to be the opposite of the A dot B value. So if you can observe here, the values of A plus B complement are the same as the values of A dot B complement. Here we have 1 0 0 0, right? Here also we have 1 0 0 0. So even if you are asked to prove this theorem using truth tables, you can just put the values here, then it will prove to you. That's we have it here and here. Then simplifying Boolean expressions. Let's simplify the expression a plus b, ab plus a negation b. We have here ab plus a negation b equals to b. Then we have a plus a complement. Then since we have said here, if it's a plus a complement, our result is equals to 1. So by the end, our result here, it will be b, because it will be b times 1. Then for the logic gate example, the expression y equals a dot b can be implemented using an AND gate. When both a and b are 1, y equals to 1. Otherwise, y equals to 0. All right, then for the canonical forms are standardized ways to represent Boolean expressions. That's sum of products, SOP, F equals to A negation B plus B dot C. So this is a sum of product. Then the one below is the product of sums.
So when you're saying sum of products, it's as good as you've got the two products like a complement b dot b, or a complement b times b, then you are adding b times c, something like that. So it's a sum of products. And then you can also have the other one, which will be a product of sum. You've got two sums and then you are adding them, something like that.
All right, say thank you. Then for the K-map, for the function f(a), ab with 1, 3, the K-map would be a slash b here with 0, 1. So here we have 0, 0. Then we have our value is 1. Then here we have 1, 0. Then our value is 1. The simplified expression would be f equals to b. Then for us, we've got an example here. It says, the question says, write a logic statement that correspond with the following logic circuit. So here we can see that we've got an A here and a B. So here, because we've got an AND gate, so here it's to be A dot B. Then here it's B, but here there is a no gate. There is a not gate. So here it will be B not. So here we've got a C, but this one is an OR gate. This one is a not gate, and this one is an AND gate. Here we've got another AND gate here. So here it's an also it's plus. So here we say our value is B complement plus C. So here, because we have an AND gate, so it's this expression here times this one. So it will be A dot B. We have this in brackets, then dot B negation plus C. So here for this expression now, our result it will be x equals to a dot b dot b negation plus c. So this is our logic statement. Then E here says draw the logic gate diagram for the Boolean expression y equals to a dot b complement dot a plus b complement. So here we can see that we have an AND gate here and we've got an AND gate here. Then here we have a no gate. So I'll draw it here. We say we have our A here and our B here. Then we have our AND gate. But if you can see, there's a complement here, so it means we have a NAND gate. So we have to put this small again for the NAND gate. Then we have this expression here. Maybe we'll just take it from here. Then we say this is an OR. So we have this one. This our so here we can have a not OR gate, which is not OR gate. So this is A plus B, not A plus not B. Then we have our AND gate. We have our AND gate here. Then we say Y. So this will become our logic gate diagram. So thank you so much. I think we've reached the end of my presentation. Over to you, sir.
Okay, I thank you for the presentations. Maybe it's now from the class if there are questions, contributions to group 7. Otherwise, you have done a good job. You've done a good job. So I don't know if you have got questions. Okay, so if there are no questions, I don't know if we have anyone from group 4. Do you have anyone here from group 4? You can admit yourself if you are in here. What about group 7? So, no, sorry, group 6. Do you have anyone from group 6? So these are the two groups who are not yet presented. And this is bad. This is bad. But anyway, thank you for the presentation from group 7. Please share that slide to my email. Share that slide to my email.
All right, sir. Thank you.
Okay. So